Hello everyone, welcome back. Today we are tackling another classic problem on Leetcode, minimum window substring, problem number 76, marked hard, but we'll break it down step by step to make it clear. This problem is part of Blind 75, a curated list of essential coding interview questions. You can find the full list linked in the description below. Be sure to check it out. Now to the problem. In this problem, we are given two strings s and t of lengths m and n respectively, and we should return the minimum window substring of s such that every character in t, including the duplicates, is included in the window. That is, we must respect the frequency of characters in t, meaning if t has two a's, this windowed substring in s must also contain at least two a's. And if we can't find any such substring in s, we must return an empty string. The test cases will be generated such that the answer is unique. Then in example 1, for the given s and t, we need to find the shortest slice of s that has at least one a, one b and one c. And one substring we can look at is this one, because it has one a, one b and one c. Its length is 6, and this can be a potential answer. Another substring is this one, which has all the characters a, b and c and is of length 8, which is not better than the previous substring of length 6. So we discard it. But the smallest substring is this one, which has all the 3 characters and its length is only 4. And since it is the smallest one, we will return it as the answer. Now, the most straightforward way to solve this problem will be to look at every possible substring in our main string s. And we can do this by running two nested loops. The first loop picks the starting point and the second loop picks an ending point. For example, starting with A, we can form the substring like A, AD, ADO and so on. And then we will do the same for other characters. So we will form the substring starting with D, O, B and every other character. And for each substring we generate, we have to check if it is a valid window. And we know that a window is valid if it contains all the characters from the target string t, including duplicates. And how can we check that programmatically? Well, we can just create a frequency map. First, say on the target string, let's call it t map, where a, b and c all occur once. And similarly, we will build the frequency map for all the substrings that we generate and check if the substrings are valid by making sure that the count of every character in our substring is greater than or equal to the count required by the t map. Here, for example, a substring must have at least one a, one b and one c as a requirement based on the t map. So for example, for the substring a, we know that b and c are missing. Same is case for substrings ad and ado, and so on and until we form this substring, which is a valid one because it contains one occurrence of each a, b and c, and its length is 6, and it can be a potential answer. But since we need to find the minimum window, we keep a variable to track the shortest valid one we have found. So here, for example, this substring adobic will be the current minimum. But we can't stop here, as we have to continue generating and checking every possible substring to be sure that we have found the absolute shortest. And much later in the process, we will generate the substring b, a and c, which is also valid and its length is 4. And since 4 is less than our current minimum of 6, we'll update our answer to b, a and c. And after checking every possibility, b, a and c will be the final answer. But in terms of time complexity, generating all the possible substrings takes O of m square, where m is the length of the input string s, since we are running two nested loops. And then we have to check if it is a valid window. This involves counting the frequency of the characters in the window and then matching it with the frequency map from t. In the worst case, substring will be proportional to the size of the original string. Hence, building the frequency map on it will take O of m time, and then comparing it with the frequency map from t will take O of capital N times, where n is number of unique characters in the target string t. But Since the comparison step is technically dominated by the map creation on the substring, we can approximate it to O of m. Hence, the overall time complexity will be O of m cube. And the space complexity will be O of capital M plus capital N, where these letters denote the unique number of characters in the input string S and the target string T, since we need to build the frequency map on the substrings and the target string T. So the brute force approach works, but it's incredibly inefficient. What's the main problem? It does a ton of repeated work. For example, when we check the window or substring adobic, we know it's a valid window, but we won't stop here. We will continue to generate even longer substring like adobeco, adobecod, and so on. And here we recount every single character we just saw and do the comparison with the frequency map of T. But we have to find a minimum such window. So instead of creating new substrings from scratch, we can use an intelligent approach that slides the window across the string, and we can maintain one single window, expand it by adding characters from the right, and once it contains everything we need, we shrink it from the left to find the smallest possible size. And this powerful technique is known as sliding window algorithm. It's a perfect tool for the problem like these, where you need to find an optimal subarray or substring that meets a certain validity condition. And this window itself is just a substring of S that we can expand and shrink. And we define its boundaries using two pointers, which we can call left and right. The left pointer marks the beginning of the window, and the right pointer marks the end, and it moves forward to explore the string. Both pointers start at the very beginning of the string, and our goal is to expand the window until it's valid, meaning it contains all characters we need, and we shrink it to find the smallest possible size. Here, for example, window has a single character, which is A, and now we have to check whether this window is valid or not. So how can we do that? And the answer is, just like the naive approach, we need to track the characters we need, which we get from string T, versus the characters we have. So for that, we will need two frequency maps, which is nothing but a hash map. So the first map stores the character requirements from string T, and we can think of it as our checklist or required map. So here, for example, we have one occurrence of A, B, and C in the checklist map, and the second map tracks the character counts inside our current window, which we can call inventory or formed map. And in this window, we only have character A with count equal to 1, and visually we can see that this window is not valid because it lacks character B and C. But how can we determine it programmatically? Well, the most direct way would be to compare these two maps. We would loop through the checklist map and see if counts in our inventory are sufficient. That is, number of characters we have in the window are more than or equal to number of characters required. But doing this repeatedly every time the window changes is inefficient, as we are looping through all the keys of the checklist map, which will result in the time complexity of O of n, where n is number of unique characters in the string T. So let's find some shortcut. Since only character A is present in the window, only the frequency of character A should be checked, because all the other frequencies remain the same. So we don't need to check for all the frequencies repeatedly. Instead, we can just use two counters. Let's call them required and formed. Required is a number of unique characters in our checklist. In this case, our checklist has only 3 unique characters, which are A, B, and C. So required will be 3. And throughout the iteration, this number won't change. And formed tracks how many unique characters we have satisfied the count for. It starts at 0. And now the logic is, every time we add a character to the Windows inventory, we check if its count is sufficient for our checklist. If it is, we have just fulfilled the requirement for that specific character. So we increment the formed count. Here, for example, frequency of character A in the window is 1, and that is sufficient that is, it is more than or equal to frequency of A in the checklist. So we increment the form to 1. So this reduces the time complexity of checking the validity to just O of 1. And a window is considered valid at the exact moment when form becomes equal to required. However, here it is not true because formed count is less than required count. So that means this window is not valid. And so only choice we have is to expand the window because this will allow us to gather more characters, hoping to eventually satisfy our checklist. And this brings us to the first major phase of the algorithm, which is the expansion phase. And the rule is simple. As long as window is not valid, we move the right pointer one step to the right, including the new character in our window and updating its count in our inventory map. So now the window has characters A and D. So we add D to inventory map. And since D isn't in our checklist, formed count remains 1 and window is still not valid because formed is less than required. So we expand the window to include character O, add it to the frequency map, and the story is same as when we added character D. So this window is still not valid. So we expand the window further and include character B in the window. And B is actually present in the checklist. And the frequency of B in inventory is more than or equal to frequency of B in the required map. So we increment the formed count to 2. And since formed is still less than required, the window is still not valid. So we have to keep expanding where we see character E added to the inventory, but window is still invalid. So we expand and include character C and increment its count in the inventory. And since C is present in the checklist and since count of C in inventory is more than or equal to the count in the checklist, we increment the form to 3 and now required is equal to formed. So that means we have found a valid window and it contains all the characters we need. So we set the minimum length we have encountered so far as 6 and the potential answer as Adobe. But our goal is to find the minimum window. And this is where second major phase of the algorithm begins, which is the contraction phase. So as soon as our window becomes valid, we do two things. One is we check if the length of this window is the minimum so far. In our case, it was the first valid window. So we set the minimum to 6 and Adobe as the potential answer. But after that, we immediately shrink the window to the left so that we can find even smaller window. And the rule for contraction is as long as window remains valid, we keep moving left pointer one step to the right. So here for example, left pointer now points to character D. And since A is now out of the window, we decrement its count in the inventory, which drops it down to 0. And since A was part of the checklist, we check if we still have sufficient A's in the window. And the answer is no because we require 1 A but we only have 0 A's. So because of this, the formed count now reduces to 2. And since formed is no longer equal to required, the window becomes invalid and the contraction phase stops. And the algorithm now knows that it must switch back to the expansion phase to find the missing character again. So we expand the window to the right where the next character we encounter is O. The count of O now becomes 2, but the window remains invalid because O was not part of the checklist. And same is the case when we add the characters D and E to the window and increase the frequency in the inventory map. But since they aren't part of the checklist, the window remains invalid. So we expand the window where we encounter character B and increment its frequency in the inventory map to 2. And even though B is now part of the checklist, formed count does not increase. It stays at 2. This is because we only increment formed at the exact moment when the inventory count for a character becomes equal to the checklist count. And since we already had one B, we had already satisfied that requirement. And adding more B's at this point won't help. So the window stays invalid and we extend the window to the right and include character A, for which now the frequency becomes 1. And since A is part of checklist and has just become sufficient, we will increment the formed to 3. And now, since formed is equal to required, the window is valid again. But the length of this window is 10, which is not better than the current minimum length of 6. So we don't update our answer. But now since the window has become valid, we shrink the window to make it invalid again. So we remove character D from the inventory, but the window stays valid. Next we get rid of O, window still stays valid. Next we remove B from the window and the count of B drops to 1, but it is still sufficient for the checklist. So the window still stays valid. Next we get rid of E and the window still says valid. And note that the length of this window is 6, equal to the current minimum but still not better than it. So we don't have to change our answer. Then we shrink the window further and L now points to character O and C has just left the window. So the count of C drops to 0. And since C is in the checklist and the count of C in inventory is less than count in required, the formed count drops to 2. And hence the window is finally invalid again. And again we enter into the expansion phase. So right pointer moves forward and includes character N. And since N is not part of the checklist, the window remains invalid. So we expand further and include character C. And so we increment the frequency of C to 1. And since C was part of checklist and the count of the character in required and inventory match, we increment form to 3. And since now required count is equal to formed count, the window is valid again. But the length of this window is 7, which is not an improvement. So our answer doesn't change, but we shrink our window and get rid of this O. Now frequency of O drops to 0, but O was not part of the checklist. So the window stays valid and the length of this window is 6. And since the window is valid, we shrink the window again and reduce the count of D in inventory to 0. But the window stays valid and the length of this window is 5. So our minimum length now becomes 5 and our answer becomes E bank. And since the window is valid, we shrink the window further, which reduces the frequency of E to 0. And this window is still valid. So the minimum length now becomes 4 and our answer now becomes B, A and C. But the window is still valid. So we shrink the window further and reduce the frequency of B to 0. And since B was part of the checklist and count of B in inventory is less than count of B in required, the formed count reduces to 2. And now since required is more than formed, this window is invalid. So we can try to expand the window on the right, but the right pointer has now reached the end of the string. So we can't expand any further. And the algorithm terminates with the answer is B, A and C. Now the time complexity of this approach is O of m plus n, because first we iterate over the string t to form this required map, which takes O of n time, where n is number of characters in the string t. And then we traverse to the string s containing m characters using the 2 pointers left and right. And the right pointer moves from the start to the end, covering each character once. And the left pointer only moves forward to make the window invalid again visiting each character at most once. Hence, the sliding window algorithm will take O of m time. Hence, the overall time complexity will be O of m plus n. And the space complexity will be O of capital M plus capital N, where these characters represent number of unique characters in the given strings. Here is a quick code walkthrough of the algorithm we just talked about, with Java code on the left and Python on right. First, we need to know what characters we are looking for and how many of each. So we create a frequency map from the target string t. In Java, we build the map with a simple loop, and in Python, collections.counter does this beautifully. We then initialize our variables. So we have left pointer at the start of the string s. Min_left tracks the starting index of the smallest valid window, and min_length tracks the length of this window, which is initially equal to infinity. In Java, we can use integer.max value, and in Python, we get it with positive infinity. Then we create the inventory map, let's call it window map in Java or window counts in Python, to track the count of characters in the current window. Let's also initialize the counters required to track number of unique characters we need, which we get from the tmap, and formed to track how many of them are satisfied so far in the inventory. Now we start expanding the window using the right pointer and increment the frequency of the character we encountered at right in the inventory map. And then first we check if this is the character we care about, that is, it is present in the checklist, and if it is, then we check if the count of it exactly matches the count in our checklist. If both the conditions match, we increment the formed count by 1. Note that we are doing exact match for sufficiency, so that when the count of this character in inventory is more than that of required, adding more of this character wouldn't help us meet any new requirements. So we only increment our counter at the precise moment of satisfaction. Also, a crucial detail in the Java code is that we use int value for the comparison, because we are storing frequency in the maps as integer objects, and if we perform the equality operation between these objects using double equal to operator, it compares the references, that is, their memory addresses, rather than their values, which can lead to bug when the numbers are above 127. So using int value function ensures that we correctly compare the numbers themselves. Python doesn't have this issue, so direct equality operator works as expected. Since now the window is valid, in the inner loop, we try to handle the contraction phase. So in this inner loop, our first job is to see if we have a new best answer. That we can check by getting the window's current length using the formula right minus left plus 1, and then checking if it is smaller than minimum length. If it is, we update the minimum length to this new smaller length and save window's starting position by setting minimum left equal to left. And next we shrink the window, where we get the character at the left pointer and decrease its count in our inventory. And after shrinking, we must check if we just made the window invalid, and that we can do by checking if the character that we removed was on our checklist, that is, it was present in the tmap, and its count in our inventory has now dropped below the required count. So we decrement formed in this case, and in any case we increment the left pointer, shrinking the window one step to the right, and this loop continues until the window is no longer valid, at which point we go back to expanding with the right pointer in the outer loop. And after the main loop finishes, if the minimum length is still infinity, we never found a valid window, and hence we will return the empty string. Otherwise, we'll use our saved min left and min length to slice the final substring from S and return it. So that's all for this video. I hope this video was useful to you. If it was, please give it a thumbs up and share it with others who might benefit from it. If you haven't subscribed the channel yet, make sure to hit the subscribe button and turn on the notification bell so that you never miss an update. Your support helps me create more content like this. If you have any questions or suggestions, feel free to leave them in the comments below. Thanks for watching and see you in the next one.